Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will begin our discussion starting from the energy conservation of a system. So before we start something new, let us recap what we learned from the last module, from the previous module. So this is our topic of discussion today: energy conservation of a system. Right, so we recap that the change in, so we are talking about a system from configuration A to a new system in a configuration B. So A and B denote the configurations. So the change in the kinetic energy between the different configuration of the system is given by the sum of the work done by each of the particles in the system, I from 1 to n, and this is time point A to time point B integration, and this is the work done by the external forces, Fi Ri dt. Right, so this is due to the external work done by the external forces. Okay, and then the other part of the net work done will be the work done due to the internal forces. So we have summation I from 1 to n, and then we can sum j from 1 to n, and this integration T A to TB, Gij dot Vi dt. Now notice that we have taken the summation to the full range, and knowing that we are going to we have an extra piece of information that these internal forces, they obey the Newton's third law, namely they will be acting along the direction of their line of interaction, and they will be equal and opposite to each other. So here in this double sum, we have possibly overcounted the contribution from the internal forces, but as we shall see later on, the overcounting doesn't really bother us much, because due to Newton's third law, the forces are going to cancel out, right? So we'll see that shortly. So then we start with a very specific case of a system where the energy is conservative, where the external forces acting on the system are conservative. So we talk about the concept of energy conservation of a system. Okay, so suppose, as I just mentioned, suppose the external fields are conservative, right? So what I'm saying is, suppose the unconstrained, when I say unconstrained, I'm talking about the external forces. The unconstrained forces Fi's are conservative fields, and we have Fi is negative grad phi I, right? So then we have this setup right now. So the external force fields are conservative, and the total work done in this case will be summation I from 1 to n integral Ta to Tb Fi Vi dt, and we get that now we are going to use the fact that the force fields can be represented in the form of an in the form of a potential function, and let us plug this information here in this integral. We see that when we plug it and then we also use the integration, we are going to get the following form of this total work done. We see that this is phi at position at configuration Ra minus phi at Rb. Notice that the original integration was from time point A to time point B, but we have this the final form to be phi at Ra minus phi at Rb, and that is because we have a minus sign in front of this potential function, this gradient of potential. So then we can sum it up, we can individual sum these potentials. So these are sum. So this was a large bracket outside. We can distribute the sum and we eventually get that this is phi, capital phi at Ra minus capital phi at Rb. So what's the difference between small phi and capital phi? Small phi are the potentials of each particle in the system, and capital phi is the total potential of the entire system, right, at configuration given by this argument. Okay, so then what we have is that phi we can, so what I just said is phi at Ri, so R1, R2, Rn is given by phi at R1 plus phi at R2 and so on, right? And we have that this is phi at Rn, right? And that is what we have. Okay. So then let us look at one specific case of this conservative force field, namely the case of object falling under gravity. So what we have is potential under uniform gravity. Okay, so this is what we have. So we want to find the potential. So this is a very basic starting example. We will have more complicated problems related to this action under gravitational potential. So to begin with, we want to find the potential energy phi when external forces on S arise from uniform gravity. Okay. So what we have is, suppose we have that Fi's, the forces are given by such that Fi is given by MIGK. So K is so we have the positive Z direction, the positive vertical direction upward is taken to be the positive K. So we put a minus sign because we know that gravity acts downward. So we have Fi, the net forces external forces acting on each particle are given by the following, and from here I can find my potential phi i's is given by, we integrate these quantities, we get that this is MIGZ, right? So the integration will be along the vertical direction. So phi i's are given by this. We have for each I we can also put a Zi, right? So this is for each particle, and then from here I can write the total potential. The the total potential. What is the total potential? This is the total potential energy phi. So capital phi is given by Mi G Zi. This is the sum over I. So this is going to be M1 G Z1 plus M2 G Z2 and so on. Right? And Mn I from 1 to capital N. So we have all these quantities up to. So this is a finite sum. Okay, so then we could possibly rewrite this expression using the concept of center of mass. So this is nothing but capital Mgz. So what is capital M? Now we can define capital M to be the following. Our capital M is summation Mi, the sum of all masses, and our capital Z is nothing but summation Mi Zi divided by summation Mi. Right? So this is nothing but capital M. So what we have is, so this is the Z component of the center of mass. So this is what do we have? So what we have shown is that the total potential acting on a system of particles, the total potential on a system of particles due to gravity is as if the potential is acting on the center of mass of the system. Right? So gravity acts in such a way that it acts on the center of mass of the system. So, so let me write what I just said. So the potential energy of any system due to uniform gravity is the same as if all its mass were concentrated on its center of mass. Right? Okay, so then, so let me now continue this idea of using the total potential for internal forces as well. Right? So what we have is, so similarly we can work up a similar idea for internal forces. So we argue that work done, remember we are working in the conservative force field frame, right? So we argue that the work done by internal forces, can be written in the form psi of A minus psi of B. What is this capital psi? Capital psi is, as we shall see, is the potential arising due to the internal forces when we assume that the internal forces are also conservative. Right? So psi of A, so we call this as this psi to be our internal potential energy. Okay, so we assume that the mutual forces Gij depends on Rij. Okay, what are these mutual forces? These are my internal forces. They depend on the position. Right? I mean, for example, this is quite logical to assume. For example, we are talking in the context of planetary motion. We know that the mutual laws of attraction, they depend on the interplanetary distance. So this is a very logical assumption. So we can write my mutual forces Gij to be Hij Rij hat, where my Rij is Ri Ri minus Rj. Okay, so then what we have is Rij can be, I can write down, so this is my displacement. So I can write down the corresponding scalar quantity to displacement as this is going to be Rij, right? And we have that Rij hat, which is the unit vector along the displacement, is given by Rij divided by Rij, right? So this is Rij bar by Rij. Okay, so then we can now see, we want to find the work done by these mutual forces. So we will have an integral of the form Gij dot Vj, right? So let us see those type of integration, or in particular, let us see those types of integrands to begin with. So we have Gij dot Vi, right? And this is now, notice, let us look at two terms together. So this is Gij Vi plus Gij, Gji. I hope to the listeners that both these conventions are clear. Gij is depends on the direction from I to j, and Gji is the opposite direction. So Gji dot Vi. Okay. So I call this as Vi, and then I will keep this as Vj. Okay, so we have the following. Now in this particular summation, I am going to use the Newton's third law, which says that Gij, I can keep Gij, and now I have inside the bracket, I have Vi minus Vj, and that's it. So where did this minus come from? This comes from the fact that Gji is minus of Gij from Newton's third law, right? So that's the idea. And then what we have is that this is going to be, remember, Gij is this quantity Hij. So this is Hij, which is a function of the mutual position, the interplanetary displacement, for example, and this is going to be, and we have the direction Rij hat, so that is my Gij. And now we take a dot product. Remember, this is Vi minus Vj, so this is going to be d dt of Ri minus Rj, right? So d dt of Ri minus Rj, and I can see that this is going to be this is d dt of Ri minus Rj, that is Vi minus Vj. So then what we have is Ri minus Rj is nothing but Rij. So that is the, from triangles inequality, that is the position, the mutual distance, the mutual displacement between the two objects under consideration. So we have that this is this quantity is d dt of Rij bar. Okay, so then what we have is that what we need, I can also convert this Rij hat here as Rij bar divided by Rij. Remember, I have used, so this is Rij hat here from the above formula. Okay, so now we have used lot of things, so let us recap everything. So after all these calculations, we will see that we get that this is Hij times Rij dot, right? Remember, we have, so notice this quantity Rij divided Rij bar d dt of Rij bar divided by Rij. So this is the velocity divided by the magnitude is going to give us the speed. So this Rij dot is nothing but the speed, right? And what else have we got? So So let us now, so this was the processing of the integrand that we are going to calculate for the work done. So now let us plug this integrand into the actual integral to see what happens. So now the integral is from TA to TB. This is Hij, Rij, and this is Rij dot. So this is d dt of Rij times dt, right? So d dt of Rij dt. Okay, so then what we have is, we can see, well, this is the work done. So Hij, Rij dot, so this is this quantity times d dt. And now what we have is integral from TA to TB, Hij, Rij times d Rij, right? And what we have is that this is going to be Hij, Rij at A, right? We are integrating this out. Remember, we somewhere we have put a minus sign. These are my forces, and we have a minus sign in the relation between forces and potential. So this is going to be, the integrand will reverse the sign. So Hij at A minus Hij at B, right? And now what we have is, so what have we done here is, we have used the fact that Hij, capital Hij is nothing but negative of integral small Hij, and with a minus sign. So that was the relation between the potential and the forces, and that brings in this change in the reversal of the values at the integral. Okay, so I'm ready to write down the work done formula for the internal with the using the internal forces. So what we have is, the work done is given by summation. Remember, we had a double sum. So double sum I from 1 to n, j from 1 to n, and we had the sum, then we had the integral Ta to Tb Gij dot Vi dt, right? And now what we see here is that this is going to be due to we see that the reversal of the sign is going to be psi A minus psi B, right? So what is this? We had to use some connection between, notice we originally we had this capital Hij in the formula. So where did this capital psi comes from? We have to define what is this capital psi. So where this capital psi is psi at this any given position, let's say R1, R2, Rn. Remember, we are talking about a configuration of n different particles. So R1, R2, Rn. So this is going to be summation I from 1 to n, and now summation, notice the change in the summation this time, j from 1 to I minus 1, and this is going to be Hij times Rij, right? So Hij, Rij. Notice that the sum is no longer from 1 to n, but from 1 to I minus 1, because the remaining ones are going to be obliterated due to the Newton's third law. The values of Hij will vanish, they are going to cancel. So we have to remove the over counting terms that I originally said in my beginning of my discussion. So let us wrap up our discussion by giving a very brief example of this setup. So the example that I have in mind is internal energy of 3 charged particles. 3 charged particles. So we have 3 particles P1, P2, P3. They carry charges carry charges of E1, E2, E3, right? And now we have to find the internal potential energy psi. So find the internal potential energy capital psi. Okay. Okay. So now we use some ideas, some inherent knowledge about this setup of charges, the inherent physical knowledge, and write down the mutual interactions between, let's say, two particles at a time. So let's say particle P1 and P2, since they carry same charges, they are going to repel each other. So they are going to repel each other with forces H12 given by E1, E2 by R12 square, right? And we have R12 is the distance between P1 and P2, right? And H12 is given by small h12. Okay. So we see that capital H12 is the following, and this is going to be integral. We continue to use these formulas. So this is going to be E1, E2 by R12 square dr12, and we integrate, we see that this is going to be E1, E2 R12. Well, we have integrated out. Okay, we have done an indefinite integration here, and so this is my capital Hij. From here I can write down my psi, capital psi. My capital psi is, we saw that this was the summation, the double sum, avoiding the over counting of capital Hij. So I can write my capital psi to be psi of R1, R2, R3 is given by E1, E2 by R12 plus E2, E3 by R23 plus E3, E1 by R31. What are these Rijs? These Rijs are nothing but Ri minus Rj, right? So these are my mutual distances between the particles. Okay. So before we wrap up, we just sum up our discussion by mentioning that we can combine all the ideas we have discussed so far. So combining ideas, we see that this is going to be TB minus TA is going to be VA minus VB, right? So what are these VA and VB? TB and TA are the kinetic energy. VA and VB was the psi, the net potential energy, the psi A minus psi B, right? So we can rewrite this statement by saying that this is going to be TB plus VB is equal to TA plus VA, right? And we see that this is what we have is the statement of the conservation of energy. So the total kinetic energy plus the potential energy at any given configuration will be fixed or conserved. So we our capital V was not psi, but it was psi plus capital phi. So this was V. So this was the total potential. Okay. So psi plus phi. The psi was coming from the internal contribution and phi was coming from the external force contribution. Everything is conservative here. Okay, so let us wrap up our discussion at this point of time, and in the next module we will continue our discussion on this conservative force field. So thank you very much. Thank you so far for listening.